Well, hello everyone, and welcome to our first online lecture. All right, so today we're going to be talking about decision trees, and I've already posted my notes on the course website, so you've probably already had a look at it. And let's get going. So let me just give you a quick outline of what we're going to do today. So we're going to give a brief introduction of decision trees and what they're all about, and then we're going to go into discussing a little bit how decision trees make predictions and how you can grow a tree, both for classification and regression models. And at the very end, we're going to talk a little bit about model variability and I guess some of the disadvantages of regression trees. All right, so what are regression trees? Regression trees are part of supervised machine learning techniques that are used both in regression and classification settings. Some of the advantages of regression trees are they're simple and highly interpretable. So that's why if you're interested in getting a quick idea or interpreting basically how your model is making predictions and the variables or the features on which it's relying to make predictions, then regression trees are a good model for that, or a good choice for that. And along the same lines, you can also visualize them, which is something that we're going to do very soon. And this helps basically understand what's going on under the hood. However, on the flip side, as we'll see a little bit towards the end, regression trees, or decision trees, I'm sorry, are tend to be highly variable, and so they suffer a little bit from the lack of prediction powers. And so that's not something to worry too much about. As next lecture, we're going to learn about ensemble models and some bagging and boosting techniques such as a random forest that will kind of help mitigate these shortcomings of regression trees. Okay, so let's get going without wasting more time. So what we're going to do is we're going to use the iris data set to illustrate decision trees in the classification setting. So if I keep saying regression trees all the time, just know that I actually mean decision trees, because I think I inadvertently keep saying that. Okay, so let's go ahead and import some of the main or standard libraries, such as NumPy, Pandas, and then some of the visualization libraries. Okay, and so let's also import, matplotlib and Seaborn. Let's go ahead and also import the iris data set. We can find it at, it's part of the scikit-learn basically data sets. Okay, so actually at the same time, let's go ahead and also import the decision tree classifier, since we're going to use it to fit the tree and also plot the tree as well. Okay, all right, we're good now. So before we continue, let's just refresh our memory of what this data set is all about. All right, so let's print a quick description of the data set. And if you recall, this data set has about, I think it's exactly actually 150 plants of 3 different categories. So the goal here typically is to try to predict, for example, the class of the plant, or the type of plant, better said, based on these 4 measurements. Okay, so although this step is not necessary. We're going to go ahead and create a data frame so that we just for visual purposes really, so that we can see a little bit better what this data set looks like. Okay. And okay. Columns, we're going to specify the columns to be feature names. And all right, let's do this. And Y will hold the target. And it's also a good practice every time you define something, I mean, to just check it. So let's check the head of DataFrame and make sure that it is actually what we expect it to be. So that's what it looks like. And Y, the target should contain zeros, ones, and twos for the 3 categories. Okay, great. So what we're going to do next is basically, let's go ahead and fit a tree and visualize the tree so that we can basically have some visual aid to explain how decision trees work. All right, so we already imported it. Okay, great. So let us instantiate the decision tree classifier. And if you click Shift Tab, you'll be able to see all the different parameters that you can choose. So we're going to use 2 for now, the max depth. We'll talk about it later exactly what it is, but basically this specifies how deep the tree will be grown, basically. And criterion, it's already by default Genie, but let's make it explicit. And what that means is that it's just the criteria that you're using to grow the tree. And don't worry too much about these terms right now. We'll discuss those more specifically in just a little bit. So let's fit the tree. Okay, so now the tree is basically fit. So what we're going to do is we're going to visualize the tree. So let's go ahead and visualize the tree first. Okay, so we're plotting the tree. So let me just write it here. Visualizing. So there are a couple of ways you can visualize the trees, but maybe, you know, the easiest one or the quickest one is probably to just use a plot tree built-in method. Okay, so let's go ahead and import that. And we can go ahead and actually just plot the tree. Before we do that, let's just specify the size of the figure. Since this is going to be a fairly large tree, let's just make it, I guess, 1810. Okay, so now let's plot the tree again. If you're unsure of the whole different parameters you can put in there or that you need, just click Shift Tab. So probably the most important one is really this decision tree, and what that means is that basically the model that you trained. So for us it's going to be tree CLF, and let's go ahead and specify max depth just because I don't want the tree to grow sort of all to the individual leaves. It will take too long. So what I'm going to do now is just run this. Okay. Alright, so I need an equal sign there. Alright, so it's not looking very pretty. Okay. And sometimes this happens, I'm not actually sure why. So what I'm going to do real quick is restart the kernel and clear the output, and it usually resets things, so they should probably work fine after this. So let me try this real quick. Okay. Yeah, here we go. I'm not sure exactly why that happens. It does every now and then, but usually, yeah, as I said, so if you restart the kernel, it usually resolves it. So now this is basically a decision tree. So all we're going to do now is we're going to just make it look a little bit prettier. So what we will do also is we'll add a couple of things. Like for example, I don't want this variable to appear here as x3 or x2. I want actually the feature name. So let's go ahead and do that. So let's run it for now. So as you see, for example, now instead of having x3 there, we have petal width and so on and so forth. So let's go ahead and also make the font size a little bit smaller. I'm going to go ahead and also show the nodes so that I don't have to count each time. True, I'm going to fill true as well. And the last thing I'm going to do is I'm going to show the actual predominant class or dominating class at each node. Okay. And this was Setosa. I don't know how to pronounce these. Okay, let's write it down. So now the tree looks a little bit prettier. Okay, awesome. So what we're going to do next is first we're going to spend a couple of minutes just talking about some of these parameters. And also, okay, so I'm going to do one more thing. So every now and then, depending like how you run it, either petal width or petal length takes precedence. I think these are kind of the major features or like the most important features that the algorithm is relying on to make predictions. However, I've already created a decision boundary for this lesson and I don't want to redo it. So what I'm going to do is I'm going to rerun this just once or twice maybe. And okay, so that's fine now. So let me just go again, depth 3. That is interesting. So that's interesting, right? So I mean, so we'll talk a little bit more later why this is happening. But anyways, so basically, more or less, like the petal length and petal width are seem to be of equal importance, and that's why they. So sometimes the tree picks petal length first, and sometimes it picks petal width. Okay, anyways. So I want this to be petal length with 2.45 because as we'll see later, as I said, I've already created the decision boundary and I don't want to replot that from scratch again. Anyways, okay, so let's discuss some of these parameters. So let's start with samples. So samples here basically represents the number of training samples of the particular attribute to that node. What do I mean? So basically, I mean, said in plain English, it just counts how many samples you have on that particular region or on that particular node. For example, here, if you focus on node 1, it's just telling us that, okay, you have basically, there's 50 training samples that have a petal length of less than 2.45. Or if you focus on node 6, for example, it basically means you have 46 samples that have a petal length of less than 2.45, I mean larger than 2.45, and a petal width larger than 1.75. Okay. And so value refers to the number of training instances in each class, so at that particular node. For example, again, let's look at node 1. So since I have value 50, 0, 0, remember we have 3 classes here, and the first class is Setosa, so the value is basically telling us that at node 1 we have 50 training samples of Setosa, type 0, 0 of the other 2 types. And if we want to focus, for example, I don't know, on, I guess let's pick number 6 again, and it's telling us that we have 0 samples of Setosa. I mean, they're all in node 1, so that makes sense. We have 1 training sample of Veriscolor, and 45 training samples of Virginsa in this node or in this region. So we'll see in just a little bit what I mean when I say region. Okay, and finally, there is this Gini parameter or Gini criteria that we use to grow the tree. So what does that mean? Loosely speaking, Gini measures the node's impurity. What does that mean? So basically, if Gini is closer to 0, or if it's identically 0, for example, it means that that particular node contains samples of only one class. So let's focus on node 8, since we've been picking node 1 all the time. So node 8, for example, has a Gini factor of 0, 0. Node 1 also has a Gini factor of 0, 0. So here, if you notice, like the vector values, you see that the first two are 0 and the last one is 43. So what that means is that this node contains a total 43 samples, and all of those are of the same class, Virginsa. Okay. So another criterion to grow the trees that sometimes is used is the entropy. So this comes from information theory, and the basic principle is similar to the Gini factor. So the smaller the entropy, the more pure the node is, and vice versa. And honestly, I think in most cases, actually, there's not a whole lot of difference between like how the tree is grown or the final tree based on what depending on which criterion you use. But you can read a little bit more, I guess, if you want to see some of the subtleties in the resulting trees, depending on which criterion you use to grow them. So just to kind of drive this point home, let's just measure the Gini factor for node 5, for example. So as you can see, Gini factor is 1 minus the sum of the squares of the proportion or ratios of the training instances of the particular class at the particular node. So for example, for G5, this is going to be 1 minus 0 over, so I have a total of 6 samples. 6, that's just 0, but I don't know why I'm writing this, but anyways. Okay. And then, so you have 2 of various color. And we have finally, this should be a 6 again. And we have 4 of the Virginsa. And hopefully we should get exactly 0.444. Okay, awesome. Now, let's talk about how this decision tree algorithm makes predictions. So suppose that you have a plant, right? And then, so the algorithm has not seen the plant before. Okay, so it's unseen. And this is a typical situation that we're interested in real life. And you don't know what type of plant that is. Say, you're plant illiterate. Let's just say that, like me. And then you ask the algorithm. So you want basically the algorithm that you fed to tell you what kind of plant that is. So the first question that the algorithm will ask you is, well, what is the petal length of your plant? And then let's suppose right now, for the sake of argument, that the petal length is 2 centimeters. Then the algorithm will move down its tree and will say, okay, you got to go to the left here, and you move to node 1 from node 0. So once you're at node 1, so actually node 1 is what we call an end node or a leaf node, because it has no more children, so it has no more depth. So at this point, the algorithm will basically will compute the proportion of each class, and then it will simply predict the plant being in the class that has the largest ratio. Okay, so in this case, it's all setosa, so it will just tell you, okay, your plant is a setosa. Now, suppose you have a second plant, just to make things a little bit more interesting now. Let's assume that your plant has a petal width of, a petal length of 5 centimeters. Okay, so again, you ask the algorithm, and everything starts always at node 0 or up top. So since your plant has a length of larger than 5 larger than 2.45 centimeters, you'll move down to the right. And then, okay, say for the sake of the argument that it has a petal width again of let's say 1.5 centimeters. So then you move to the left here, and then let's say that you have a petal length, I think we said 5 centimeters, so now we have to go to the right here. So you end up at node 5. And then again, the algorithm will count essentially all the samples and keep track on which the type of each training sample at that particular node, and it will basically predict by majority vote, which in this case is a Virginza. Now, speaking of predictions, sometimes we are not interested directly in having our algorithm tell us exactly what class the new data should be put on, but rather to give us the sort of a vector of probabilities, sort of or likelihoods that the new data point or the new plant in this case is in one category or the other. And we can also make it so in effect both ways are reasonable. And in the second case, instead of giving us a single number of 0, 1 or 2, it will actually give us a vector of probabilities. So for example, let's just compute the vector of probabilities for node 5 here. So it will be something like this. Since I don't have any setosa, it will just be 0. And since I have 2 out of the 6 samples are various color, and 4 out of the 6 samples are Virginza, it will give us this probability vector. Okay, awesome. So now let's briefly discuss about so at this point, what I want you guys to do is maybe, just pause the video and just pick another sort of plant with different dimensions and just run down this tree and see if you can predict. Okay, so let us continue with visualizing the boundaries. So what do I mean by that? All right, so here's what I mean by that. So essentially all we're doing here is so this is a simplified version really. Since we have 4 features we cannot see in 4 dimensions, but since we saw from the decision tree that the algorithm was relying most on petal width and petal length, let's just use these 2 features to kind of create a scatter plot and try to plot the decision boundaries. Okay. But normally in 4 dimensions, these lines would be hyperplanes. So, but in this case, I think we don't lose much actually. Okay, so yeah, these are these regions that we kind of talked about. So these are the end. So these regions that we see here are the end leaves or the end nodes here, basically, like we have node 4, 5, 7, and 8. And as we can see, these are actually pretty accurate. Okay. And I think this is node 7. I didn't write it there, but anyways, okay. All right, so an important question that we need to address is how is this tree created? Like this is also what's known like a tree growing algorithm. And so, in other words, how does the algorithm decide to pick petal length and this 2.45, for example, splitting value on the first node? Why not pick something else? Actually, as we saw when we ran it the first 2 times, I think initially it picked here petal width and 0.8. So why is that happening basically? Or here, for example, why is the algorithm picking, for example, petal width and 1.75? Okay, so bottom line, the algorithm picks a combination of the feature and a splitting value such that it results in the least amount of impurity here on the next stage. So in other words, to put some math behind what I just said. So the algorithm or the model will search for the pair where x is the feature and tx is the splitting point that minimizes the following loss function. And I want to point out here that this is not the only loss function that you can use. So here, this GLGR stands for the Gini factor on the left node and Gini factor on the right node. This ML and MR are for the respective node sizes here and here. For example, if X was petal width and TX was 1.75, then G left would be in this case 0.168, G right would be 0.043. And so the idea is that it picks this number and this one such that this weighted sum here is as small as possible, or is it an optimum. And as I said, instead of using the Gini factor here, you can use also entropy, and honestly you can create your own sort of reasonable loss function as well. Okay, so this is it for classification trees. So what we're going to do next is we're going to switch gears just a little bit and talk about decision trees in the regression setting. And to illustrate this, basically these concepts, we're going to use the insurance data set that we used in one of our projects. I think it was a first project. So the underlying mechanisms between classification trees and regression trees are very similar. They differ in some small and subtle ways, which we will talk about shortly. But before we do that, let's just go ahead and read this data set in. And because I don't care about sort of optimizing a model or choosing the best model so far, I'm going to go ahead and drop every row that has a missing value. Okay. Drop any. Okay. So let's check real quick but whether we have any more missing values by just plotting a heat map. Heat map. Okay, so insurance is no, it's true. Okay, so as we see, there's no more missing values. Let's just check the shape and see how many guys we have there. So we have 871 data points. And in what follows, we're just gonna do some of our standard pre-processing steps, like splitting up our data frame into features and target, and then just converting these qualitative variables into numerical values. Okay, so let me just do this reg so that I don't override the feature values that I previously wrote. Not that it matters, but just in case I want to go back and rerun a cell from previous computations. Okay, let's do a drop. Charges. X is 1. So we've done this multiple times. So I'm just gonna go ahead and do this. And again, as I said, it's a good practice to always just check the head and see that what you expect to see actually is what you see or what you get. All right, so let's go ahead and convert these qualitative variables into numerical values. And so here we're just going to record the columns that we want to convert, and they are sex, smoker, and region. And we're going to use the, so you can basically use the apply method with a lambda function, but we're just going to use a dummy, like get dummy values. dummies. Okay, so data is going to be xreg, and columns are going to be, and I'm going to drop the first one. Okay, great. So let me actually call this and check the head again. Okay, great. So that's basically what I meant by converting the qualitative variables into these numerical values. Awesome. So what we will do next is, just as we did before, we're going to fit a regression tree, and then we're going to visualize the tree. And then we'll talk about a little bit about how the regression tree is grown and how predictions are made. So these are the only two sort of small differences between the classification tree and the regression tree. Okay. So without further ado, let's go ahead and then import the decision tree regressor. Okay, so tree regressor, and the parameters, again, if you click Shift Tab, you'll get all the parameters that you need. Just as before, we're only going to specify the depth and the criteria. Although the criteria is by default MSE, like the mean squared error, we'll just keep it like that as well. I mean, we'll just make it explicit, but you can use other criteria if you wish. Tree reg, so let's fit it. And, you know, okay, let's see what's going on here. Classifier. So we need the regressor here. Okay, cool. And I'm not here, so for when you use these ensemble models, especially like decision trees, they handle nonlinearity well, and it's not always necessary to actually scale your data. And in this case, I actually don't want to scale the data because I'm more interested in sort of interpreting and sort of relating exactly how the algorithm is making predictions in regard to the features or feature values. Okay, so let's actually plot the tree. So what I'm going to do now is I'm just going to go ahead and copy paste this so that I don't waste too much time doing writing the same things. I need to get rid of these classes now, as we are dealing with a regression problem now. And these columns need to be the regression xreg, because that's where our insurance data set is. And this is tree reg as well. Okay, I think this is okay now. Awesome. So the only thing I guess I'm going to do here is I'm going to make this font size a little bit smaller. And I guess I'm going to make this a little bit larger so that I have a bit of separation down here. Okay, anyway, so this looks good. So since the mechanism is kind of the same as before, let's talk real quick about how this would make predictions. So let's suppose now that a new person, so again, remember this data set was about predicting the insurance charges based on these six characteristics or six pieces of information about a person, okay? So let's suppose that I come in, I'm a new person, like the algorithm has never seen my data before. And let's see what would the algorithm, for example, predict about me. So it asks me, okay, are you a smoker? I say, well, no, I'm not a smoker. So it goes right to the left here, down to the left from node 0 to node 1. And it asks me the age. So what's your age? I'm like, okay, I'm younger than, it doesn't, so it basically asks me, are you younger or older than 43.5 years old? So, okay, I'm younger, so I go right to the left. And then it's asking me again. So see, age is being used again at this point. So are you younger than 32 and a half? I'm like, okay, yes, I'm younger than 32 and a half. So it goes down all the way to the left here. Now, once you're here on the leaf node, how does this algorithm decide about what to predict? So pause the video here and just think a little bit to on your own if you can try to figure out a reasonable way that the algorithm would predict. Okay, so first off, notice that on this node, at this stage, or on this region, there is a total of 252 people or sample or training samples. Okay, in other words, there is 252 people that are not smokers and that are younger than 32.5 years old. So what the algorithm will do is will simply take the mean or the average insurance charges of these 252 people and predict that as my sort of insurance charge. In other words, the algorithm would say, okay, your insurance charge is about $4,110. Okay, so this is basically one of the main differences between regression and classification trees. So here we don't have different classes, but it's a continuous target variable, so it just averages over them. Okay, so now the only other question that we need to address as far as regression trees go is how are they grown? And the procedure, again, the underlying mechanism is very similar to classification trees. The only thing that differs is the loss function or the cost function that you optimize. So here, instead of looking for a pair of features and split values that minimize the weighted average of the Gini factor or entropy, here you minimize the weighted sum of the residual sum of squares. And again, this is not the only loss function that you want to use. You can use, I don't know, mean squared error, maybe R2 squared, and like a couple of other loss functions that you can write yourself actually. Okay, so the last thing that we need to address is this variability. So one thing that I want to mention before I go there is this bias-variance trade-off. So here I think I should probably add here model variability and bias. So first off, let's go back here to this decision tree. Now imagine what would happen, for example, so if a new point, so when you get a new point, the new point will fall in one of these 1, 2, 3, 4, 5 regions, right? And then if it falls here, basically you'll just predict by majority voting whichever class is predominantly or dominates that region, basically. Now imagine if you grew deeper the tree. So what would happen here? So if you grew this tree to a depth of 10, for example, we'd get a lot more splittings of these regions, right? So now if a new variable came in, right, then to predict the class of that particular plant in this case, you'd look at a fewer number of your neighbors, right? So what that means is that actually the model itself is more variable because it's relying on a fewer number of its neighbors, and it's prone to overfitting. Okay, so this is kind of something to keep in mind. So and that's why when you're looking for maybe the best model, you have to use the depth of the tree as one of the hyperparameters, because the deeper you grow the tree, the more likely you are to overfit. But you decrease the bias, so that's why you got to keep that in mind. So that's kind of what we're going to do here actually. So we're going to sort of try to look at model variability and the bias variance trade-off as a function of the depth of the tree. Okay. Great, so let's go ahead and do that. All right, so what we're going to do is we're going to use cross-validation to basically get a feeling of the variability of the model as well as how it reacts to the depth of the tree, different depths of the tree. Model selection, import, cross, validate, and k-fold. Okay, so what we're gonna do now, let's see, let's create a k-fold first. Let's do n splits 10. Let's do shuffle true and random state. Let's do a random state of let's fix it to 42 first. Now I'm gonna create a dictionary here where I will store sort of so what we're going to look at as a result is the R2 scores. So this depth here is a dictionary. It's going to contain, so the keys of this dictionary are going to be the depths, for example, depth 2, 3, 4, up to 10. And the values are going to be the R2 scores obtained from cross-validation. Okay, so that's a plan. So let's build a for loop here. So for I in range, and let's start, depth 2 and go all the way to 10. So we're not interested in depth 1. And so let's do tree, cross-validation, cross-validate. And here we need to put in the estimator. So we're going to use a decision tree classifier, actually a regressor. And so max depth here has to be variable, and we're just going to let MSE be the criteria used to grow the tree. And so what we want next is the cross-validation number. So basically this is F. It's going to split the data set into 10 and randomly do that. So let's actually, I think the data needs to be here somewhere. So after the estimator comes the data. So let's do that. And so what else do we want? Scoring. So we're just going to do R2. I think for now this is probably okay. And so now we're going to store this. Let's do depth. Let's see. And this is going to be CV, tree CV, test. So we want to return the test R2 score. Let's see. What's going on here? I'm not sure what's going on here. Let's see. Okay. Yeah, estimator. I guess it doesn't want it that way. Okay, this is good. Alright, so let's just check the depth. So as I said, so let's actually go ahead and create it. Excuse me. Let's go ahead and create a data frame so that it's easier to view it. It's prettier, really. So let's see what it looks like. So this data frame, so each column here contains these the R2 scores for that particular depth. So there's 10 of them because we had 10 splits. All right, so let's go ahead and create a box plot. Okay, 14.6. Set style. Okay, I don't know why I hit enter. So let's do now SNS box plot. Not box, box plot. And what we will do is data df. Let's do this for now, and then we'll see. So I guess we can just make this look a little bit prettier if you wanted to by making the font of the X ticks a little bit larger. For example, okay, and let's do the same for the Y ticks. And let's also put a Y label there. And also a title. So this is maybe bias. Okay. Maybe let's just do decision trees. And Bias-variance trade-off. Okay. Let's, I guess, increase the font size, and they're basically done now. So one thing to note, though, is that the deeper you grow the tree, on average, basically, you have a higher variability. Let me look at this. For example, in your depth 9 and 10 is pretty variable. So these are the R2 scores, like the 10 R2 scores. So it goes all the way to a little over 60 to all the way almost 95. And as we can see that actually, a depth 3 or a depth 4 are probably the ones that result in the how to say this, they're more robust, I want to say, I guess, and they're less prone to overfitting, it seems like it. And actually, if you wanted to test for the variability a little bit more, then you can also maybe rerun this with rerun this. For example, maybe change the random state here at the k-fold and use that as well as a hyperparameter to get an idea just how variable the model is. But this gives you kind of a good idea of how variable this model is. Okay. And so next class we'll also learn how to save the model and load the model so that you don't have to retrain it. It is not an issue here, but when we deal with more like ensemble models that take a long time to be trained, and you really don't want to retrain your model every time you load your notebook or you load your code. So you really want to be able to save all the parameters and the weights and everything, coefficients of your model, so that you can just load them and make predictions. So we'll learn how to do that. Actually, I did that in my solution of project 2, so you can check it out there as well. So this is it for this lecture for now. What I want you guys to do now is use the airline data set to build a classification model using decision trees. Okay, let me... decision trees. So basically, the airline data set was the one that we used in project 2. So see if you see, just compare the results on what you get using decision trees versus what you get using logistic regression and KNN that you did on your solution of project 2, basically. Okay, well, this is it for now. So thank you for listening, and I will see you next class. Bye bye.